All right, good people. This is the last method of how to find the derivative of an inverse function. I do want to say, if you'll allow me to move this out of the way, I do want to say this is kind of the calculus default way of finding it. And so, just to recap, method number one said if you're trying to find the derivative of the inverse function and you can find the inverse function, then do what you learned in Algebra 2 pre-cal, find the inverse function, and then take the derivative. Method number two said if you can't find the derivative function, at least start the process, switch the x and the y variables, and then take the derivative implicitly. And then depending on which value you needed, you're going to have to plug in that specific value to figure out the answer. And that's what we did in examples 3 and 4. But now we're saying there's a pattern that occurs. And the pattern that occurs is even if we don't know what the function is, but we know some information and we can't find the inverse function, or it's not an inverse function, it's an inverse relation. There's a pattern that emerges that we can figure out how to find the derivative of the inverse by doing this. So I need to have a function that's differentiable, right? And therefore the inverse function is also differentiable. And as long as the input of my, let me see, as long as the input of my function evaluated derivative is not equal to 0, then we're okay. And so we have two different versions here. I'm going to focus on the second version. I think the second version might be a little bit clearer. So because it differentiates our two functions. We have an f function, which more than likely you will be given. And then you have the g function, which is the inverse of f. And so we know that if we have an inverse function, our input and our outputs are backwards, right, from the original function. And so this says there is a pattern that emerges. And the pattern is the derivative of the inverse function, the derivative of g, is just the reciprocal of the derivative of the original function evaluated at the original x coordinate domain. Now this is going to be a little bit And so to kind of deal with that, I'm going to over here on the side. I'm going to say this is usually what I help myself remember, which is for the g function, we are given a point in example 5 that has an input of 2 and an output of -1. But remember, g is the inverse of f. How do I know that? Oh, it tells us right here. G of x is the inverse of f. So the original f function has the point -1, 2, right? And so what this says is there is a shortcut because there is a pattern, and the pattern is if I'm looking for the derivative of the inverse, the derivative of g, just take the derivative of the original function, but I'm going to plug in not the input of the inverse, I'm going to plug in the output of the inverse because that's the input of the original function. And if you remember back in the first video, that's what I was trying to tell you, that if whenever I'm dealing with a function and its inverse, the x and the y coordinates change, right? Well, the domain of the function of the original function is not the same as the domain of the inverse function. As a matter of fact, it's the range of the original function, the inverse of the domain of the inverse. So all of that to say that if I'm looking for the derivative of the inverse function, if I'm looking for g prime of 2, I can find the derivative without having to find the inverse by just saying it's 1 over f prime, but this is where I have to be careful. It's not f prime at 2 because 2 is the input of the inverse, which is actually the output of the original function, and I'm taking the derivative of the original function, so I need the input value, and the input value is actually -1. So in this formula that you see over here, notice how they remind us that if we're given the original function f, and if we're given a point on the inverse function g, where I know my input x of g, I know my output value y of g, then remember that the y output is the input of the original function. And because I'm going to take the derivative of the original function, I need to know what that input is. So it's actually the output of the inverse. So if you look at my blue writing over here, what I'm trying to say is, if we're going to take f prime, I need to plug in the input of f. But if they give me only this piece of information, then I need to focus on the y coordinate, because the y coordinate of the inverse is the x coordinate of the original function, which is what I need in order to evaluate it. And so that's the tricky part of the shortcut. The shortcut itself, hey, that's a neat shortcut, because all I have to do is take the derivative of the original function, 3x squared plus 4x plus 0, and then evaluate it at -1. So I'm going to take that derivative function, and I'm just going to plug in 3. I'm going to plug in -1, so that'll be 3 times -1 squared plus 4 times -1, and that's going to give me my derivative at the same point of the inverse function. So that's going to be 1 over, I believe this is 3. I believe this is -4, and 3 plus -4 is -1. And so therefore, my derivative is -1. Now again, we have to be careful. If you look at this purplish box, we're taking the derivative of the inverse. If we know the formula for the derivative of, if we know the formula of the original function, then what I can do is I can take the derivative of the original function and take the reciprocal, as long as I evaluate it at the correct point. And the correct point is going to depend on the information that's given. Let's try example 6, and then I want to go back to the other side of the paper and maybe try to do this shortcut with some of the problems we already did, like the straightforward way without the shortcut. So let's look at number 6 and see if we can find out what they're talking about. F is a differentiable and it's an increasing function. So the y values, the outputs are always getting bigger. Selected values of f and its derivative are given in the table. If g is the inverse function of f, okay, so now we know g is the inverse function of f. What is the value of g prime of 6? So we're looking for g prime of 6. And so what we just said and what we saw in that green box is that if I'm looking for the derivative of this, then I need to evaluate that or I need to find 1 over f prime, but not f prime at 6. I need to find the coordinate that goes with it. So now let's think about what this table tells us. This table gives us nothing about g. It only tells us about f and f prime. So when I think of g, we have an input of 6, but we don't know the output. And so in the world of f, that means I don't know the input, but I know the output. Oh, f, when my output is 6, my input is 3. So this number is the number that I need to evaluate my derivative of the original function at. He said grammatically incorrect. But all we're doing is we're looking for the derivative of the original function, evaluated at the point that we're talking about, and then taking the reciprocal of that. So that's why I have 1 over, because I'm flipping it over, 1 over f prime of 3. Oh, but we know f prime of 3. When x is 3, f prime is 2. So therefore, my answer is 1 over 2. And that's it. We found the answer. This shortcut, helpful. It really is. It saves us time because we know that there's a pattern. In the next section, you're going to see that pattern appear, And my goal is to make it a little bit more explicit of the connection of this pattern when we talk about the derivatives of inverse trig functions. Okay, so the big idea, when I'm taking the derivative of an inverse function, if they give me the original function, take the derivative of the original function, evaluate it using the point that was given and the appropriate input, and then flip it over. That's why it says 1 over f prime, because I'm flipping it over. So here my f prime at 3 was 2, but I flipped it over, and that's how I got 1/2. So then the question is, can I do the same thing with the ones that we've already done that we already know the answers to, right? So let's see. I want to find, so I'm going to go back to example 1. I'm going to just find a color that I didn't use. How about orange? I'm going to use orange here for example 1. We were given the original function, but we're asked to find the derivative of the inverse at 7. Okay, so let's see. I'm going to say, I said I was going to use orange. So we have G, and we're given the point 7 comma, something. I don't know what that something is. But then I'm going to go to F, and this point is something comma 7. So again, what I need you to understand and remember is from all the work that we did with inverses in Algebra 2 and Pre-Cal, that the input of the inverse is the output of the original function. So they gave me the input for G, but it's actually the output of F. I'm looking for the input of F because that's what I'm going to plug into my shortcut formula. How do I do that? Well, if I know this is 7, then that's my output. So then this is going to be 7 equals x to the third minus 1. And then I'm going to solve for x because I'm looking for the x coordinate of the original function, which is the output of the inverse. So I add 1 on both sides, take the cube root of both sides, and it turns out this value that we were looking for here is actually 2. That's the number I'm going to plug in. Where am I going to plug it in? I'm going to plug it in to the derivative of this equation. So I'm going to take the derivative of x, the derivative of f at x is 3x squared minus 0. I don't need to write the 0. But now I'm going to evaluate that at 2 because that's the number that we're talking about. That's the point at which we're talking about. And so I'm plugging in the 2, and if I evaluate this, I believe I get 12. Oh, but we were looking for the derivative of the inverse. Well, the derivative of the inverse at 7 is just the flip of whatever the derivative is at that same point on its domain, and we got the same answer. A shorter method for sure, but a method where I have to be very careful about which value, the value that I'm given, is it in the domain of the inverse or is it in the domain of the original function? And most of the time, the value that they're going to give you, like in example 1 here, this x value is in the domain of the inverse. So then you have to go backwards to figure out the x value that's in the domain of the original function. Once you figure that out, the formula is pretty basic because you just take the derivative of the original function, plug in your x value, your appropriate x value, and then just flip that answer over, and you get that pretty quickly. And that's the third method of finding the derivative of inverse functions.